A thin vertical wire fixed at the top with a horizontal rod attached below. At one end of that rod hangs our brass sphere. This wire acts like a spring, twists the horizontal rod, and it resists, snapping back to its resting position when released. The more you twist it, the greater the force required. Let's dive deeper. When we twist the rod by an angle theta, the restoring torque, the twisting force, is proportional to the angle theta by which it rotates. Torque equals K times theta, where K is the torsion constant of the wire. Now, the force F acting on the sphere, which is keeping the wire twisted at an angle theta, is the same force the ball exerts back. Using basic physics, we know that the torque is equal to the cross product of the distance from the center and the force applied. So, torque is equal to R cross F, which equals R times F sine alpha, where alpha is the angle between the horizontal rod's length from the center and the direction of the force. If we manage our experiment such that the force is always perpendicular, as sine of 90 degrees is 1, we can get rid of the sine term. So F equals torque divided by R, and as torque is K times theta, F equals K times theta divided by R. To shield our experiment from air currents and humidity, those pesky interferers, we enclose it in a glass jar. Markings on the jar help us measure angles accurately. The lid has a hole for the torsion wire and another on the side for inserting a fixed brass sphere on a rigid rod. It stays put, no wobbling. Measure the initial distance between the balls when uncharged. We will denote it by R. First, ensure both spheres are neutral by grounding them. Charge a glass rod with silk, touch it to the fixed sphere, then let the two spheres kiss briefly. Now, each carries an equal charge, let's call it Q. The stage is set. Let the electric dance begin. Remove the fixed sphere and note the initial position. Now, insert the charged one. Watch the suspended sphere twist away, repelled by the like charges. Here's the simplified diagram for our setup. Measure the twist by measuring the angle theta from initial position. Let's record our data. For R equal to 20 centimeters or 0.2 meters, theta equal to 3 degrees, or about 0.052 radians, and assuming the torsion constant of wire K equal to 0.283 and capital R equal to 1, the force F is roughly 0.015. To vary the distance R without changing charges, twist the torsion head at the top. It resets the neutral position, bringing the spheres closer or farther. Take more readings at different R values. Plot force F against R. It drops off sharply like an exponential decay. But wait, compare it to 1 over R squared. Perfect match. The electric force is inversely proportional to the square of the distance. Eureka! One piece of the puzzle. Now let's vary the charges while keeping R constant. Bring in a third neutral brass ball. Touch it to the fixed charge sphere. Charge halves, now Q by 2 on the fixed one, while the suspended holds Q. Measure the new theta and force. Repeat by sharing charge further, halving again and again for more data points. Plot force against, say, Q1 plus Q2. Nah, that's messy. But F against Q1 times Q2? Straight line through the origin, so F is proportional to the product of the charges. Combine with our distance finding, we get F is proportional to Q1 times Q2 divided by R squared. Introduce a constant K, and we have Coulomb's law F equals K times Q1 Q2 divided by R squared. This K, mind you, is the Coulomb's constant, not our wire's torsion K. It's a universal value tying the electric universe together.